This is Physics 2212, Lab 1, Charge Tapes. My name is Arishi Mooney. Let's get into it. So, what is the purpose of this lab? Well, it's to observe the interactions between two pieces of electrically charged tape and approximate the amount of excess charge accumulated on each piece of tape using our observations. The materials used are Scotch tape, a meter stick, a flat surface, and cardboard cups for support. A preview of the results found in this experiment are shown here. Now, before we begin, let's go over some fundamental physical principles. The first one is Newton's second law, which states that the net force acting on a system is directly proportional to the system's change in momentum. Next, we have Coulomb's law for electrostatic forces of attraction and repulsion between two charged objects. Finally, we have the law of universal gravitation, which describes the attractive gravitational force felt by two bodies of non-zero mass separated by a distance. We also have the charge of a single electron down there, and it's important to note that the law of conservation of charge must be followed, and it is, as that is how we're able to make our observations. The initial measurements and calculations can be shown to the left. Now, in order to set up the experiment, I took a 20 centimeter long piece of tape and stuck it to a table. I then took another identically long piece of tape, stuck it on top of that, and peeled it off to give it a charge, as can be seen by how it was attracted to my finger. In order to determine the sign of this charge, I recorded the interaction it had with an object of known charge, which in this case was a negatively charged pen that I had charged by rubbing through some wool. As seen in the video, the interaction is attractive, indicating that the piece of tape gained a positive charge by peeling it. Because I was able to conclude a piece of tape acquired a net positive charge by following the outlined steps, I was able to observe the interactions between two positively charged pieces of tape. In my experiment, tape B was the system, while tape A and the rest of the universe were the surroundings. Once the system, or tape B, had reached equilibrium in the y direction, I measured the distance between the two tapes to be 0.022 meters. Now, we're going to go through these 4 steps to calculate the electrons lost by tapes A and B. First, we begin on calculating the gravitational force acting on B, which is the mass of tape B times the acceleration due to gravity here on Earth, as shown. Now, let's look at the free body diagram for tape B. Because it's in equilibrium in the y direction as it's levitating and not accelerating, there's no change in momentum, the electrostatic repulsive force due to A on B must be equal in magnitude to the force of gravity felt by B, as seen. We can then use this value and the key assumption that A and B are assumed to have the same amount of charge to compute that charge, and therefore we can find the excess charge on tapes A and B. We can then use that excess charge and divide by the absolute value of charge per electron to get the total number of electrons lost per each piece of tape. We can then divide that number by the total number of atoms to get the number of electrons lost per atom in each piece of tape, as shown. Shown here is the glow script program I wrote to model this experiment, and it serves as an ideal representation of the experiment and the procedures followed. The important parts are highlighted in green, and it should also be noted that the values calculated were accurate by the glow script model and match the experimentally calculated values. And that can be seen here with the charged piece of tape and the ratio of electrons lost to the number of atoms. We did have to make some assumptions to make this experiment more feasible. First, we assume that both pieces of tape have their charge uniformly distributed about the entire piece, and that such charges are equal, and that the entire piece of tape can be reduced to a single point charge located at the tape center. We also assumed that the only forces present were gravity and the electrostatic force of repulsion, neglecting air resistance, friction, and any other external forces such as those due to external charges. This leads to some errors, the first one being loss in charge in each tape due to grounding. Touching the tape with the surroundings or handling it without care will make it regain its lost electrons, therefore neutralizing it, or decreasing its overall charge. The tapes are also not uniformly charged. An unequal distribution in this leads to varying strengths in the magnetic field contributed by A at various locations in B. Now, let's do some analysis. What if the electrons had a positive charge and protons had a negative charge? Well, nothing would actually change it in this experiment. Although the charges on each tape would now be negative, and therefore their electric fields would point in the direction opposite the tapes in this experiment, they would still have the same magnitude of charge and the same sign. Therefore, they would still apply the exact same repulsive forces on each other. And they would interact same with the charged pen from earlier. Why is it important to handle the charged tapes as little as possible? This is to prevent grounding and the subsequent neutralization of the charged tapes. When you contact the positively charged tapes or make them touch the environment, they try to regain the electrons they lost. As such, handling them without care or making them frequently touch the surroundings will cause them to gain the electrons they lost back and become neutralized, preventing us from observing the electrostatic interactions present. Thank you.